So I'm very happy today to introduce Soledad Villar. So she got her PhD from UT Austin with Rachel Ward, and she's had a few positions since then at the Simons Institute, both in Berkeley and NYU. And she's now an assistant professor at Johns Hopkins University in the Applied Math Department. Her research interests are in machine learning, optimization, graph neural networks, and equivariant machine learning, which is the topic of this talk. So I'm very happy to have her talk to us about equivariant machine learning from classical physics. So thank you.
Okay, thank you so much for the invitation and for being here. I'm going to talk about equivariant machine learning. And so this talk is in the context of deep learning. Machine learning models that in the past year have achieved the state of the art and surpassed the state of the art in many fields, including image classification, reinforcement learning for playing games like Go. They have beat the best human players. And recently there has been a breakthrough about machine learning models that can do protein folding or predict how proteins will fold. And I'm not going to talk about deep learning per se, but this is in the context of that. And one of the properties that these machine learning models have is that they use a lot of data and that they're very over-parameterized. So you have more parameters than data, and you are using that for learning behavior from data and predicting. So in this context, these machine learning models that have been so successful have the property that they have more parameters than data points. So many possible functions that you have in your hypothesis class of functions can fit the training data perfectly. So you can fit the data perfectly. So which one is the right one? How do you make it so that you don't overfit? And so there's a concept that they have in this deep learning community that is called like inductive bias, which basically means that, well, you design your class of functions so that when you do local optimization in that class of function, you converge to a local minima, because you don't know that it will be global, that has good properties. And with good properties, you mean that it has good generalization properties. So not only fits your data perfectly, but also it works well in data that you haven't seen before. That's it. So, by the way, I'm happy to take comments or questions throughout the talk if you have some. So, how do you design your class of functions so that they have nice properties? And so one can look into the literature of these deep learning models that have appeared in the past, like that had kind of reappeared in the past 10 years. And basically the model that was very successful and kind of made like a revolution in machine learning was these convolutional neural networks. And these convolutional neural networks have the fact that they use these filters, and these filters are designed to exploit some rotation symmetries and like small translation symmetries as well. This class of functions of convolutional neural networks are equivariant with respect to translations. And if you look at other methods that also have been successful in the past 10 years, like the recurrent neural networks are also, I'm not going to define what they are, but they also exploit some sort of translation symmetry in text. And graph neural networks are designed so that they exploit some symmetries on graphs as well. So one of the claims is that exploiting symmetries is a good way to give you a good inductive bias for your class of functions. And I'm going to show you how to do that and some examples and how, and maybe it'd be useful. So, so in the physical sciences, there are like two types of symmetries that one can encounter. The symmetries that come from like the regularity of the physics. So symmetries that one can observe from like doing experiments on a physical system. Symmetries that come from, for instance, from conserved quantities, like conservation of energy or conservation of momentum. There's this theorem by Emmy Noether that relates the conserved quantities with the symmetries in physical systems. But there are also other symmetries that come from like not the word itself, but the mathematical representation that we decide to give to the word. So given the word, I mean, it exists there. I choose some coordinate system to describe it. The choice of coordinates is definitely not unique. There's many set of coordinates that I can choose. And then this, like, if you want to be agnostic with respect to the choice of coordinates, then that's a symmetry that you need to impose. And so the claim is that if you're going to do machine learning for the physical sciences, you want to respect these symmetries. You want to do machine learning models that are invariant or equivariant with respect to coordinate transformations, units, gauges, and also if you're doing it for like a specific problem like protein folding, you also want to use the actual symmetries of the active symmetries of the problem, which are like rotation and so on. So how do we do this? Okay, so first I'm going to define like invariance and equivariance. I'm going to say that I have a group, and this group acts on a data set. And so I say that a function is invariant if every time that I apply a group element to the input, the function doesn't change. So f of g times x is equal to f of x for all g in the group and x in my data set. So for example, this dumb example here, I have a classification problem. This is a rows. If I rotate it, the classifier doesn't change. So it's invariant with respect to these discrete rotations. And also, I want to consider equivariant functions, which basically also requires that the group acts in the output. And so a function is equivariant if every time that I act by the group on the input, the output is acted by the same group element. So the action in the input space and the output space doesn't need to be the same action. They can be, you can use different representations, but basically that's it. Yeah. And so, for example, say that I have this particle system and I want to predict how this particle system would evolve in time. And this particle system satisfies that if I do a rotation to the input, then the prediction should rotate in the same way. And so that's an equivariant function. So what does equivariant machine learning does? Basically, it parameterizes the class of functions so that for every choice of parameters, when you do gradient descent or to find your optimals, for every choice of parameters, the function in the space is invariant or approximate invariant or equivariant or approximate equivariant with respect to the group action. So for every choice of parameters theta, I have an invariant function. And so how do you do that? And how can you do machine learning in this context? What kind of results can you get? And that's basically the questions that I'm going to address today. And so as an example, I'm going to give you the example that have to do with graph neural networks, because I know that Sasha is interested in it. So basically the idea is the following. Okay, so I have a graph. So this graph can be represented as an adjacency matrix. And when I'm going to do machine learning on this graph, I'm going to use a representation of the graph as a matrix. And so the way I can express this graph as a matrix is not unique. If I do a permutation of the rows and the columns, I get another matrix that is equivalent, that represents the same graph. So basically, the functions that I want to learn on this graph, as written as functions of the matrices, need to be invariant with respect to this action by permutations or by conjugation, or equivariant if I'm learning, for instance, an embedding of each of the nodes in dimension D. Like, so I guess there's two tasks that I can think of: graph classification or node embedding. And so the question is, how can we efficiently parameterize the space of functions that satisfies this property, the invariance or equivariance? And so there's a huge literature in graph neural networks that defines different classes of functions that satisfy these properties. But the issue is that if you want to write a class of functions that satisfy these properties, it would be hard to be able to separate non-isomorphic graphs in some cases where the graphs are, in some cases, the class of functions, in order to separate non-isomorphic graphs, you may need to have many parameters, and that would make something that is not super efficient for machine learning. So there's a question of, can you have a class of functions that is expressive enough that it can separate orbits, and also you can implement it efficiently for machine learning? So there's many questions in that space, and And so there's a very natural connection between graph-neural networks and invariant polynomials, which is what Sasha and I are working on together, right? Anyway, so, but this is, I'm not going to talk about graph-neural networks today. I'm going to talk about other kind of equivariant machine learning that has to do with applications to images and particle systems, the graphs next time. Last time that I came, I talked about graph-neural networks. So, so basically, the idea is the following. In this talk, I'm going to explain how to implement equivariant models on particle systems, in particular with respect to simple E groups like rotations and Lorentz groups, and also some other groups like scalings and permutations. And then we are going to show you how to implement equivariant functions on images as well, if I have time. And there's a few applications that I'm working on with collaborators in cosmology and computational biology. That's basically the idea of the talk. And if you have questions or comments, please let me know. So our target was to parameterize functions that are invariant or equivariant with respect to some group action. So how do you do that in practice? So the first attempt is to use data augmentation. Data augmentation is something that is very common in machine learning. In data science, you can just like incorporate like new training examples that satisfy the symmetries and then use that as like a proxy to do the symmetries. Another thing that you can think of is like exploit the fact that you have conserved quantities to add penalizations that kind of promote the existence of symmetries. But what I'm going to explain today is how do you do it using like kind of like a restriction of the class of functions to the functions that satisfy the symmetries. And so, and I guess that you get something nicer if the class of functions that you obtain in the end can express all the equivariant functions or can approximate all the equivariant functions. And so in the past years, there have been a lot of papers that design machine learning models that are equivariant. In particular, the methods that people use are something called weight sharing, which is similar to something called message passing that has to do with like how people implement functions on graphs. And there's generalizations of that to images. And also there's some methods based on irreducible representations. There's some methods that kind of constrain the class of functions to restrict, to kind of learn the invariant functions as a set of constraints. And there's the way you can do it using invariant theory. And so I'm going to explain the main approaches and give some examples. So this is the equivariant architectures based on some papers by Risi Condor and Maron and collaborators. And the idea is to extend the classical feed-forward neural network to work with equivariant functions. So are you familiar with the classical feed-forward neural network? So the idea is that a classical feed-forward neural network is a composition of linear maps with nonlinear equivariant functions. So you take your input, this is a vector that, I don't know, it's an RD, and then you apply a linear map, and then you apply a nonlinear pointwise function like a ReLU, like for each of the entries. Then you apply another linear map, etc. And that's basically how the function is defined. So what you learn are the weights of the linear maps. So you basically learn the linear maps from data.
Affine or?
You can do affine, yeah. Mm-hmm. Yeah. And so the main idea, the first idea is, okay, what can we do if we replace the linear layers by linear equivariant or invariant layers? So basically linear functions that satisfy that. And so, yeah. And then this has two issues. The main issue is that there are not that many linear invariant functions. So think about like, if you have like a linear function that takes a vector and is rotation invariant, then you don't have that many options. So that kind of reduces the expressivity of your class of functions. And also the other question is like, how do you design this nonlinear, the pointwise function so that it's compatible with the action, so that you don't lose the equivariance. And so if your action is by permutations, then that's very easy. But other groups, you don't know, you have to figure it out. So the solution that these people, Condor and Maron, proposed is to, in particular to the first issue, which was like, you don't have many nonlinear, you don't have many linear equivariant functions, is to extend the action to tensors. So now instead of looking at functions that go from RD to RD, I'm looking at functions that go to the tensor of RD with itself k times and goes to the tensor of RD with itself k prime times. And so you look at the functions that are linear and equivariant from here to here, and then equivariant with respect to the action defined on the tensor. So basically you take your tensor product and you decide that the action is like in each of the entries of the tensor in the same way. And so the question is like, okay, now I'm going to define linear functions on tensors. How do you parameterize the linear functions? So the answer is you use representation theory, and in order to do that, you will need to compute some Clebsch-Gordon coefficients, which may be hard to do in practice, but the idea is the following. So basically what we are going to say is that we are going to say that this RD to the K that we had before, this RD to the K is a representation of my group. And we're going to use the fact that we're going to use Shor's lemma. We're going to take our space, decompose it in the irreducible representations, and we're going to parameterize all the linear equivariant functions by just looking at how this group decomposes in, how this vector space decomposes in irreducible representations. So the idea is that, okay, you can think of it as group representation is a way to see your group multiplication as matrix multiplication. And you know that if you have a representation is an action from your group into the linear transformations of a vector space, you say that something is a subrepresentation if it takes a subspace and sends it to the same subspace. And Shor's lemma tells you that if you have a representation and you decompose it in irreducibles, then a linear equivariant map between two irreducible representations is either the identity or zero, or like a multiple of the identity or zero. So if I have my vector space, my tensor product vector space, and decompose it in the irreducible representations, like here, then just by looking at doing that for the input space and for the output space, looking what irreducible representations match, allow me to decide that how to parameterize the equivariant linear function between these two spaces. Is that clear, more or less? Does that make sense? Okay, so basically you take your input space, your output space, decompose it in irreducibles, and from there you can read how to parameterize the linear equivariant functions. The issue is that how do you do this decomposition of like your product, tensor product representation that you had before in irreducibles? And in order to do this decomposition, you use the Clebsch-Gordon coefficients, which may be hard to compute, but for some groups, they're known and can be, yeah. And this is actually implemented in some software. So for instance, there's a paper by Fuchs and al. And Thomas Smith and al. That implement this method for SO3, and they show, for instance, that this approach is universal if you allow the order of the tensors in the intermediate layers to be arbitrarily high, and that's like a consequence of the Stone-Weierstrass theorem, because you can think of it as like these tensor spaces are kind of like polynomial spaces that are equivariant. Okay, that's that's it. How am I doing on time? I'm 20 minutes in. So any comments or questions? I can. So another way you can do this that is slightly different, but mathematically is equivalent, but you know, like even if mathematically is equivalent, you can you get in machine learning, the way you write things is important in order to get what solution you have, because even though maybe the class of functions may be the same, a different parameterization of the class of functions would end up with like a different solution because of the way you implement the stochastic gradient descent. So since the problem is not convex, different parameterizations of the same thing would give you completely different solutions, which is something very interesting, and there's a lot of work in that regarding like over parameterized machine learning. Okay, so another thing that we can do is, and I'm going to show you this example with like this little particle system that I have here. So say that I have this particle system and I have n points in RD, and maybe these points are like vectors in RD that maybe correspond to positions and velocities of these particles. So say that I want to predict something of this dynamical system, say the energy. So something that we can do is we can try to parameterize the functions that take n vectors in RD and output a scalar, so that they are invariant with respect to different groups, like the rotations or Lorentz or the orthogonal group, etc. So we can use like classical invariant theory, like the first fundamental theorem for invariant theory, that says that a function that takes n vectors in RD and goes to R is OD invariant, so invariant with respect to rotations and reflections, if and only if it is a function of the inner products of the input vectors. So this is like these inner products are the generators of the algebra of invariant polynomials, and also you can use the fact that polynomials are universal in order to say that these are functions, that if a function is invariant, is if and only if you can write it like that. So so basically this suggests the following like machine learning model that allows you to do that. So then you take n vectors in RD, take the features, which are the scalar products of the input vectors, and then you learn an invariant function. Any function that you learn from the scalar products are going to be invariant, and every function that is invariant can be written in terms of the inner products. Right. So that's, and the same thing can be done for other groups by using what are the generators of the invariants for the other groups, like the Lorentz group or rotations. They have more, like since rotations are a subgroup of the orthogonal group, they have more invariants that you have to add and things like that. Okay. So from here, we can parameterize the space of equivariant vector functions using the fact that, well, you can prove it, you can write it in this form. So if you have a function that takes n vectors in RD and outputs a vector in RD, say, for instance, the position of a certain particle or the velocity of the center of mass or something like that, this function is equivariant with respect to the orthogonal group if and only if you can write it as a linear combination of the input vectors where the coefficient functions are scalar invariant functions. So they're functions of the inner products. Okay. And so this suggests like the following kind of like design for your class of functions. So you take your inputs, the vectors in RD, then you compute the scalars, which are the invariant features. Then you learn the functions of the scalars, these F1 through Fns, like the linear combinations, and then the output is going to be that, the linear combination of that. So this basically allows you to have a simpler parameterization of the class of equivariant functions that does not require you to know how to do the decomposition on irreducibles. but you need to know what are the invariants. So sure, like so it's known, like you can know the invariants for some groups that we know, and for other groups that are harder to compute. But for these examples, they're examples that come from classical physics, there's no need to compute the Clebsch-Gordon decomposition. You can just do it in this form, and that's like simpler, basically. And there's a lot of tools from invariant theory that can go into the design of machine learning models, and you can get simple implementations and things like that. So one interesting question is, so if you are interested in like the data science part of this problem, is that when we started, we had like n vectors in RD, and then in order to learn the equivariant functions, what we do is we compute the matrix of inner products. So we go from n times the n times the inputs to like n square features. So is that something that we can afford, like have n square features in your model? So I don't know, that depends on you, but something that you can use is the connection between the fact that with the low rank matrix completion literature that tells you that if you have a matrix of inner products like this, like all the matrix, and you only observe the things that I have in green, then you, with high probability, you can reconstruct the entire matrix using convex optimization. For instance, there's some papers that like Amit Singer, he has these papers on like this rigidity theory of graph matrices that tell you when you can reconstruct a low rank matrix from observations. So here, this is a n by n rank D matrix. So you could reconstruct it with a subset of that has size n times D plus 1. But also, if you're doing machine learning, you don't actually need to be able to reconstruct the whole matrix of inner products. So you can have your features to be a subset of this matrix, and then since you know that there exists a unique reconstruction, then you can just learn it as a function of these fewer features if you want it. So that's that's something that can be done. And if you look at other, like, okay, so I gave you the example with the SOD, which was like a linear combination of the inputs with the scalar features. Then if you, OD, like if you look at SOD, the rotations, then you have more invariants, you have more equivariant functions, and these equivariant functions come from, for instance, one example is like if you have in the sphere, you take the cross product of two vectors, that is an equivariant function that is not, it's an SOD equivariant function that does not lie on the span of the inputs. And those are the only other equivariant functions that you can get that come from the generalized cross product. And you can write like a full parametrization of all the equivariant, SOD equivariant functions that you can get using that. So this is a very classical thing. And you can use very simple extensions to extend this to translation equivariance and also permutation equivariance. So say in this particle system, it didn't matter like the order of the particles in order to predict the center of mass. So so then you can write it as a function that is invariant with respect to permutations, and then you can work out how does the function look like, and this function can be expressed as some form of message passing. Well, like the coefficient function is the same for all the functions that show up in this linear combination, but is like a function of the thing that is multiplying and everything else. It's like you can write it as message passing. And so this is actually part of like something that you can write. Like there's like some classical work by Malgrangi that was, well, we couldn't find the citation to this actual work, but Gerald Schwartz told Ben that this work was by Malgrangi, and then there's some paper from the 70s that reference it, but we couldn't find exact citation for this. But there's like an explicit way that you can write the equivariant maps from the invariants. And the idea is that, and maybe that's a question for Peter, maybe you know about where this comes from. Yeah. So basically the idea is, okay, so if we have, if we have a group acting on a vector space and the group acting on another vector space, then there's a natural action, which is the group acting on the space of maps from B to W, and the fixed points of the action are going to be the equivariant functions. So we can think of the equivariant functions from B to W as invariant maps from like B times the dual of W to R. And so the knowledge, if like in the case of the action of the orthogonal group on copies of vectors, if we know what the invariants there are, then there's like a natural, like this natural transformation allows you to parameterize the equivariant functions from vectors to vectors, right? So because we know what the invariants in the space look like, and here the action in the dual is the same because it's orthogonal group. So with that, you can construct an algorithm that allows you to look at the equivariant, like allows you to construct the equivariant maps from the invariants, which basically relies on the fact that, and maybe I'll show you how it works with an example, and then the general algorithm would make sense after that. So the example is the following. So the example is actually the example that I have already proved. Okay, so say I have a function that takes n copies of a vector space and outputs a vector space, and this is an equivariant polynomial. And so I can define, if I take another vector in my vector space, then I can define an invariant function, which is it takes these n original vectors and my new vector that I took, and then I say, well, my invariant function applies the equivariant function, and then it takes the inner product with the new vector. So this function is invariant. And so it's an invariant polynomial on copies of the space. So it's a function of, in the case of the OD that I explained before, so it's a function of the inner products. So it's a function of the inner products with the original inner products that I had before, and the inner products with the new vector that I introduced, right? So these polynomials, so this function over here is actually an homogeneous polynomial of degree 1. So then I should be able to write it in terms of a polynomial combination of the original things and these new inner products that generate the invariants here. And so after that, I can just cancel out these two guys, and I get that the function that I had before was going to be a polynomial combination of my original inner products times my original vectors. I don't know if that makes sense. So basically, this is the proof technique from Lagrange that can be extended into an algorithm that computes the equivariant functions from the invariants. That is very easy in the case of OD, but it can be more complicated depending on how the polynomials of degree 1 invariants on the last coordinate, on like the dual, the space that we took the dual, look like. So that's the idea. So we have, so we consider the polynomial generators of my algebra of invariants, and then we take the polynomials that are degree 0 in W star and the polynomials that are degree 1 in W star, and these ones are the ones that are going to show up in the parametrization. And basically, that's the way you do it is you would need to take, just like this division that I did here, this canceling out, can be done by taking the derivative with respect to the second coordinate on this polynomial expression. And basically, that's it. You get like polynomials of the ones that were degree 0 times the derivatives of the ones that were degree 1. That's the idea. Okay, maybe I went too far with this explanation, but I hope you appreciate it. But that's just one of the things that is interesting, because it kind of like is something that is very classical that can be used in like machine learning now. So I like that. So after that, I'm going to show you a few examples and then more. Okay, so far I show you how to parameterize the equivariant functions that take a vector, that take vectors and output a vector. And so I'm going to show you how this example look like in this specific toy example, where I have like two masses connected with springs, and I want to predict the dynamics of this guy. So my data includes the positions and momentums of the original part of the masses, and the problem is to predict the dynamics. So if I look at this problem, so this is a toy example, and it's a Hamiltonian system where the kinetic energy and the potential, like the Hamiltonian is the sum of the kinetic energy plus the potential energy, and that's a conserved quantity. And this conserved quantity is like in correspondence with a time translation symmetry, in the sense that if I observe the system right now and it's like this, the dynamics are the same as if I observe the system tomorrow and it has the same state. Okay. And so this system has a symmetry that is like, you have these pendulums in 3 space. And so if I do a rotation in the XY plane, then the prediction should rotate the same way. But if I do a rotation in the Z axis, then the prediction should not rotate in the same way, because there's gravity, and the gravity affects the potential energy. However, if I introduce the gravity vector as one of the inputs in the machine learning model, or like in one of the inputs of my function, then the function becomes O3 equivariant. Because when I rotate all the masses, I rotate the gravity vector with it. And that's one form of like passive symmetry, like one of the symmetries that had to do with like the coordinate freedom, like, right? So I do a change of coordinates, and then the system doesn't change. So with that, we can implement this model as an O3 equivariant model, not just an O2 equivariant model, by just adding the gravity as one of the inputs to the learning. And so here I want to learn a function that predicts from like positions and momentums. It predicts the positions and momentums after a certain time. So the way we can do it is by using neural ODEs, and that's something that we discussed earlier today. So the idea is the following. So I take my data and I say, well, my data will satisfy a differential equation. I don't know what differential equation it satisfies, but I'm going to parameterize, I'm going to learn a function that learns what differential equation the data satisfies. Then I'm going to use a solver, like an ODE solver, to predict the outputs for that differential equation. And then I'm going to look how do the predictions compare with the data, and then make an update to the parameters that define the differential equation. That's the way it works, the neural ODEs. So you can do that, and you can know, okay, this is an equivariant model, so the differential equations should satisfy the symmetries, the O3 symmetry that I just told you earlier. And you can implement it like that. Another thing that you can use is the fact that this system is Hamiltonian, so it conserves energy, and it satisfies a specific differential equation that you know of, which is like there's a Hamiltonian, which is a scalar value, and then you know that it satisfies a specific differential equation that you can integrate using a specific integrator, a symplectic integrator, and that is another symmetry that you can incorporate to your problem, to your modeling. And the claim is that the more symmetries that you implement, the better the learning, right? And so we have some examples and that kind of like show, and this example is in this toy example, which is this double pendulum, you can see that the more symmetries that you implement, so the larger the group, so here this group has no symmetries, but there's no group here, it's just like an MLP. The more symmetries that you implement, the smaller is the error. And so this line is a neural ODE, and this line is a Hamiltonian neural network that implements the Hamiltonian symmetry. And so you can see that you obtain the smallest error with you have the most amount of symmetries, which makes sense. And also there's some math that you can do to just like quantify how much do you gain for by imposing the symmetries. And I'm gonna show you like one specific example of that. Okay. Comments, questions? Did you see the neural ODE before? Was it? The fact of maybe I can explain it again if you want. Okay. Okay. So. So these are discrete subgroups of the orthogonal group. So they're finite. Yeah. I don't know. That's a good question. Yeah. Yes. Yeah. Yes. Yeah. So this one didn't like work that well. So maybe there's like, I don't know. Yeah, more symmetry this way. Oh yeah, these ones are not in order. Yeah. Yeah. So another symmetry that we can implement in this model is the symmetry with respect to units. Okay, because so we're predicting an energy which has units kilograms meter squared divided by second square. So if I do a transformation to my inputs so that everything that had units of kilograms now has units of pounds, then the outputs should transform in a predictable way. Or everything that had units of meters now has units of yards, whatever. There is like a specific group action that comes from units transformations, which is a form of scaling with respect to different variables that is scaled with different exponents. But here, like if you have k units, the action is by like r greater than 0 to the k. That's the group that acts. And so the question is, how can we parameterize the class of functions that satisfy these symmetries? And the answer is in a classical dimensional analysis. The idea is that you can take your input features, and then you can compute some dimensionless features that basically is just like you cancel out the units, you construct features that divide things and multiply things so that all the units cancel out. Then you can construct a basis of these dimensionless features, and then you can learn the function from the dimensionless features, and then with a fixed scaling, you get the output. And that is one way you can implement these units equivariance. And that's the definition of like, yeah. So, and then you can see numerically, you can see that when you implement these units equivariance, you get gains that you can learn, you can train in one set, and then generalize to a different set. And the reason, like one of the reasons is because like you can think of it as there's your domain, and then you can take the average of maybe. You can take the average of like the domain through the group action, and that would give you an invariant domain. However, in the case of the scalings, that doesn't make sense because the group is not compact, so you may have some difficulties there. But so until what time is this talk? Okay, so yeah, 5 minutes. Okay, yeah. So I'm gonna say this, and then I'm gonna end. So the one question that you may ask is, how much do you gain by imposing these symmetries? And so there's many ways you can quantify it. One way that you can think of it in the context of regression is you can look at the risk, or like at the error that an invariant function makes in comparison with another invariant function that is not invariant. And basically the idea is the following. Say that your group is compact and your data is supported in an invariant distribution, and there is a target invariant function that you don't know, and you do some regression and you obtain some other function f. So you define the risk of f as the expected value when your data is sampled from the data distribution of the value of f minus the true y square. And so the generalization gap is going to be the difference of these risks. And so you can compare what is the difference between the risk of your function f and the risk of projection of f onto the space of invariant functions, and the actual, like, the fact that this group is compact and the measure is symmetric tells you that this difference is actually the norm of the orthogonal complement of the projection of the function onto the orthogonal complement of the space of invariant functions. So it's always greater than 0. And in cases where you don't have that, then you can do some symmetrization in order to compute like how much you gain in order to, like, how much you gain by imposing this symmetry. And you always gain something just by assuming that your target is invariant. So if you project it to the space of invariant functions, then you're going to be closer to the target in the case that, there's some key property that goes into this theorem, which is the fact that if your measure is invariant, then the natural projection onto the space of invariant functions, which is the Reynolds operator, which is like averaging over the group orbit, corresponds to the orthogonal projection with respect to the measure of the data. And that's what made that computation works. But this is not true if the group is not compact. And so there's like some complications there. And in practice, in equivariant machine learning, one does not like do some regression and project into the space of invariant functions, but one does like a definition of the space. The definition of the space already includes only invariant functions. So then there's not like a knowledge that I know of that allows you to do that directly, like to quantify how much better it is to do the regression in a space of invariant functions versus just like do a regression and then project onto the space of invariant functions. But yeah, that's it. So, and I work with people in astrophysics that apply these to cosmological simulations. I'm not gonna go into the details, but if you have questions, I'm happy to discuss afterwards. And I'm going to say, well, and there's some extensions to images that I will not discuss right now, but just let me summarize and tell you that I believe that enforcing the exact symmetries in machine learning models give you the correct model assumptions, give you better sample complexity, smaller generalization error, and there's like a lot of beautiful math that one can do while doing that. And in particular, the symmetries in classical physics can be implemented using very classical invariant theory, and you can do it for classical Lie groups, you can do it for units, and there's a nice explicit translation between invariance and equivariance, and we can extend this to vector and tensor images, which I did not discuss, but I'm happy to chat afterwards. And these are my references, and this is it.
Thank you for the nice talk. Are there any questions from the audience? Also, people on Zoom can feel free to ask questions by typing them into the chat box or into the Q&A. So can I ask, with the CNNs you showed at the end, this is rotational invariance?
Yeah. So if you want to make a CNN rotation equivariant, then you need to use invariant filters. Basically, that's the idea. So if you make your filters to be rotation invariant, then the corresponding convolution is equivariant with respect to these discrete rotations. And so, yeah, if you have a vector field, then you can generalize it using filters that are vector filters or tensor filters that are also symmetric with respect to this action, or maybe they have a different parity but similar.
There's lots of different approaches to this. I think I've seen a lot of different papers on equivariant CNNs and so on. So is this somehow the same as what I see in the other works is just adding a bunch of additional filters, so that you take a filter and all of its rotations as well, or something like this? Or is there something else?
Is it, I mean, no. If you allow them to have different coefficients, like if you have a filter and a rotation of the filter and you allow them to have different coefficients, then the output is not necessarily equivariant. But if you use symmetric filters, it is equivariant. And there's actually it's a theorem that if you have like any equivariant function can be written as a convolution with a symmetric filter.
Yeah.
I think that, you need to be in an homogeneous space, and you need that the stabilizer of every point is the same. Yeah. Mm-hmm.
You can say a bit about the stuff with the dark matter and the galaxies.
Oh, okay. Yes. Okay. I can say more things about that.
Sounds really interesting too.
So yeah, this collaboration started because I was at the Center for Data Science at NYU, and I was working with David Hogg, and he is an astrophysicist, and he wanted to do some machine learning model for astrophysics that had this rotation equivariance. And so we looked into the literature, and we only found the ones that were using the rules of representations. And we were like, well, there must be an easier way to do this. So from the physics, the physics intuition, they have this intuition every scalar can be written in Einstein summation notation. Every scalar can be written in terms of inner products and outer products. So then we went back and we saw, well, it's actually the same as saying that the invariant polynomials can be generated by the inner products in SOD. And so with that, we designed a different model, and that is very classical things. And then the main point that he wanted to do was he had these dark matter simulations that can be very large, but they can be computed quite cheaply because they only use gravity. And there's other simulations that are called hydrodynamic simulations that are way more expensive to compute. And so what he wanted to do was to use these cheap simulations to predict properties obtained by the expensive simulations. And so what features would he use in this machine learning model? Well, he wanted his features to be invariant with respect to units and with respect to rotations and all. And so we came up with this model, and we designed these features that are basically take the simulation that they have, which is a big particle system. They do some binning on the particle systems, and they compute moments of these of each of these meanings, and then these moments are computed as tensors, and then they're compressed using like this Einstein summation notation, and then they get all these features that look like this that are invariant with respect to rotations and units, and they use that for making the predictions, and they obtain that it performed better, significantly better than the state of the art that they had at that moment. So that's the story.
Okay, interesting. Thank you. Are there any other questions people have? Yeah.
Mm-hmm. Yes. So, okay. So I have that up here. So the invariant, so did I write the group action? No, I didn't write it. But basically, an element X has a vector of units. Which is like K units. For instance, if you have like energy has a value and it has like 1, 2, -2 as a vector of units. And so if I say that if I have like λ1, λ2, λ3 act on X, since these are the units of X, then these act as X to the λ1 times X to the λ2. How is it? No, it's like λ1 to the 1 times λ2 squared times λ3 to the -2 times X, right? So it's like, if I scale the units of meters by λ1, then in the output, it scales like λ1. And if I scale the units of the one that has units of meters, meters by λ1, then in the output it should be λ1 squared, because that's how the units work in that case. And so in order to find the dimensionless features, what you do is you solve like basically you ask, how do you multiply your features so that the units cancel out? So it's basically you write your features as a product of your features with like these coefficients, so that when you do a linear combination of the units with these coefficients, that linear combination is equal to 0. So it's basically solving a linear system over the integers. That's it. Yeah.
Always want something invariant, and sometimes you also want it to be invariant.
Mhm.
But having it both equivariant and invariant is very restrictive, you know.
So, I mean, invariance is a particular case of equivariance when the action in the output is trivial. But
Right.
a function is,
Trivial, right.
yeah. So, I mean,
So you're then restricted, right? So do you ask both of them to be invariant and invariant? Because then, as you said, we need to
no. So I think that I don't really understand your question, but like,
are you requiring just cases where you require both, you know, you got to be both equivariant and invariant?
no.
No, okay, because
Usually, if it's invariant, it's automatically equivariant.
no, you have
But
no, only no.
no,
Because
sorry. No.
Is if it's equivariant, you can think of it as like, okay, an invariant function is an equivariant function where the action in the output is trivial.
right,
Yeah.
then it's a trivial, right? So it's a
Yeah.
problem. You restrict it to the kind of function that you can work with.
No, but I think that, I mean, it's it's the same thing. It's just invariance and equivariance is kind of like the same thing if you understand that the connection between these two things are
You can.
like,
but
yeah.
It's just a small thing that it requires both of them. You cannot have them both of them to satisfy. So sometimes.
Yeah. So one function, in order to be equivariant or invariant, you need to know what the action in the input is and the action in the output is. So
Right, so I'm just kind of, so for example, when you do clustering, you want it to be both invariant and equivariant, or you give up on equivariant, or?
what is the output of your clustering?
So.
Okay, so one example. Okay, I have an example. So you give me a data set, and what I'm going to do is I'm going to assign each of these points to clusters. So I'm going to say these points belong to this cluster, this point belongs to this other cluster. Okay, so if I give you a permutation of that data set, the clustering should permute in the same way. So that is equivariant. The clustering is equivariant.
Equivariant.
Yes.
Right, but if you want it to be also invariant.
With respect to what?
So, you want it, you know what, let's discuss.
Okay, we can
Also-
discuss afterwards. Yeah,
sure.
yeah. Yes, okay.
Okay, any other questions? All right, if not, we'll thank Soledad again for the nice talk.
Okay, thanks.
Follow up with you on this, but I think for clustering actually we need the invariance itself, but we'll go over example.
Okay.
So,
So, oops.
Discussion, but
Uh-huh.
we have a colloquium going on
Okay, that's good. Yeah.
immediately.
Okay.
What's your schedule
I
later on?